Hi there and welcome. This is the third video in the series about harmonic oscillators. In the first two videos, we covered the simple undamped oscillator and the oscillator with damping. I've put a link for those videos in the description. In this video, we will add an external driving force. Let's first set up the system again. We have an object of mass m attached to a spring. As usual, the spring is characterized by a constant k. The origin of the coordinate system is at the equilibrium position where the spring is relaxed. There are basically three forces acting on the system. Restoring force following Hooke's law. Second, there is a damping force, for example due to friction or air resistance. And the physics behind these forces were already discussed in the first videos. What is new here is the third force, which is external driving force. And this could be, for example, a short impulse. We can imagine hitting the oscillator with a hammer or applying some other sudden force. Or we can imagine grabbing the left-hand side of the spring and moving it back and forth. The system will somehow respond to this external disturbance. And this response to the external disturbance will be the focus of this video. Okay, as usual, what we need to do is solve the equation of motion. And Newton's second law can be written in this form. We have a mass times acceleration equal to the net force acting on the system. The net force is the sum of all the forces, which includes the restoring force, damping force, and the driving force. Now, in general, the solution to this differential equation can be written as the sum of two parts, the so-called homogeneous part and the particular part. The homogeneous part of the solution is the solution to the equation with a zero right-hand side, meaning when there is no external force. And we have solved this in the previous video. This is the equation. We know that the homogeneous part can be written in this way. When we consider, for example, the case of subcritical damping, we can express it as a cosine function with the exponentially decaying amplitude. The particular part of the solution will be the solution to the original differential equation with a non-zero right-hand side. And this particular part of the solution will be our main focus, because it will depend on the specific form of the driving force. So in order to solve this, we must specify the form of the external force. And as I already mentioned, we can consider various types of forces. An impulse type external force can have, for example, this kind of profile. The force is zero, and then at specific time, t prime, we hit the system with a hammer, which is represented here by this sharp peak. And after that, at a later time, the force becomes zero again. This force can be represented, for example, by a Gaussian function of this type. Another type of driving force could be, for instance, if you take left-hand side of the spring in your hand and start moving it back and forth. The profile of the driving force could take a form, for example, of a cosine or sine function with some driving frequency omega. The faster you move your hand back and forth, the larger the value of the driving frequency and vice versa. In general, when considering an arbitrary type of driving force, the particular solution to the differential equation will not be easy to find using analytical methods. When we are lucky, the solution can be expressed at least with the help of some special functions. Usually we solve this type of equation using the method of Green's function. And this is slightly advanced topic, I will not discuss it here, but it may be the focus of another video in the future. Anyway, using the Green's function method, we can in principle solve this equation for an arbitrary type of driving force. However, when doing this, we often encounter some complicated Fourier transform integrals that still cannot be evaluated analytically, so we are still forced to do numerical integration or use another approach. In that case, it is just easier to solve differential equation numerically from the start. The point is that usually one has to solve the problem numerically. But when an external driving force is of this type, meaning harmonic force, there is an analytical solution. And from now on, we will only consider this type of driving force. This type of driving force actually contains very interesting physics, particularly the phenomenon of resonance, which we will discuss at the end of this video. Okay, let's consider the special case of a harmonic driving force. We can express it using, for example, cosine function. And now if you remember for the first video, we discussed that harmonic functions can be written using Euler's formula as a complex exponential functions. Working with complex exponential functions is easier than working with trigonometric functions like sine and cosine. So we will use complex exponentials now because it will simplify the math. However, we will keep in mind that only the real part of this complex function has physical meaning. Using this form of driving force, the differential equation for the particular part of the solution looks like this. Now there are various methods for solving this, and this can be found in most basic textbooks on differential equations. But we are physicists, not mathematicians, so we will try to solve it the physicist way, if you will. And what is the physicist way, you may ask? We will basically guess the solution. How does one go about guessing the solution? Well, on the right hand side of the equation, we have a harmonic function. We may now ask ourselves what kind of function must be on the left hand side so that the equality holds at all times. Well, it must also be harmonic function. There is no other choice. So our guess for the solution is the harmonic function, written again using complex exponential. The important thing here is that it must contain the same frequency omega, which is the frequency of the driving force. The capital X0 is just some complex amplitude, which is unknown for now. We can now plug this solution into the differential equation and see if it works, and then find the value of capital X0. Okay, we will do that, but what comes next will require more lengthy mathematical operations, and I will not cover those in great detail. They are just some elementary operations that anyone should do as exercise. What I will do, however, is simply show the intermediate steps and comment on those results. First, we need the first derivatives, which are shown here. We plug those into the original equation, and what we get is this equation. We cancel out the exponentials and see that the capital X can be written in this form, indicating that it is some complex number. And what we want now is to decompose this x0 into its real and imaginary parts. And here is the results. This is the real part and this is the imaginary part. You can do this by using this trick. When you have a complex number in a denominator, you can multiply it by number 1 of this form. We can plug the expression for a capital X0 back to the original form of the solution and obtain the particular solution. The particular solution written in this form is a complex function. However, we recall that only the real part of the expression has physical meaning. So in order to obtain displacement of the object as a function of time, which is the physical quantity we are interested in, we need to take the real part of this expression. And one has to be careful here because the real part is not simply the term involving the cosine function alone here. And this is due to the fact that x0 itself is a complex function. So with a little bit of algebra, we obtain the real part of this expression, which can be written in this form, where the coefficient a and b are defined here. Alright, this is luckily almost all the math we are going to do today. Let's now take a look at some simulations to see what the solution looks like. As we have discussed at the beginning of this video, the complete solution to the differential equation with the external driving force is the sum of the homogeneous part and the particular part. The homogeneous part of the solution can be written, for example, in this form, in the subcritical damping regime. When we are not working in the subcritical regime, this solution is not valid, but that doesn't actually matter. What matters is that the homogeneous part always decays away after a sufficiently long time. And we saw this in the previous video on damped harmonic oscillator without external driving force. So it doesn't matter which regime we are working with, whether it is overdamping, critical damping, or underdamping, it always decays away. Next, the particular part of the solution is written here. We just calculated it for the case of a harmonic driving force. The important thing is that a particular part of the solution does not depend on the initial conditions. The homogeneous part does depend on the initial conditions, but the particular part does not. Instead, the particular part depends only on the form of the driving force. The form written here is valid only for the harmonic driving force. For different driving force, we would get a different particular solution. In the case of harmonic driving force, a very important parameter is the value of the driving frequency omega. And we've also discussed how the nature of the solution depends on the frequency of the external driving force. Before we do that, here is what the solution actually looks like. The red line represents only the homogeneous part of the solution in the subcritical damping regime, and we can clearly see oscillation with decaying amplitude. The blue line represents the full solution, the sum of a homogeneous part and a particular part. And we see that after a sufficiently long time, the homogeneous part is practically zero, and we are left with only the particular solution. The particular solution oscillates with the same frequency as the driving frequency, except at the beginning, right? At the beginning, the frequency of the oscillation is not the same as the driving frequency, and this is due to the presence of the homogeneous part of the solution. How does the solution look like in the case of supercritical damping? We can recall the solution of the damped harmonic oscillator with no external driving force. And this is the homogeneous part of the solution, and we have seen in the previous video that the solution decays exponentially with no oscillations. The full solution with a harmonic driving force in this regime then looks like this. Because the homogeneous part rapidly decays, the full solution becomes practically equal to the particular part very quickly, and the presence of the homogeneous part at earlier times is almost not visible. In the case of subcritical damping, we have an oscillator behavior, but the amplitude of this oscillation decays exponentially. The full solution with the harmonic driving force then looks like this. We see that at the beginning there is some irregular behavior due to the presence of the homogeneous part in the subcritical damping regime. However, at sufficiently later times, the full solution is practically equal to the particular part. The homogeneous part of the solution is often referred to as a transient solution, and this is because it depends on the initial conditions and typically decays over time, vanishing after a sufficiently long period. The particular part of the solution is usually called a steady-state solution, and this is because it persists indefinitely and represents the long-term behavior of the system, and it is independent of initial conditions. Alright, now that we have convinced ourselves that the transient part of the solution is not important after a sufficiently long time, we can focus only on analyzing the steady state part of the solution, because that is what actually matters in the end. The steady state solution for the case of a harmonic driving force with frequency omega can be written as a sum of sine and cosine function with the same frequency, and the coefficient a and b are defined here. We can say that this coefficient also depends on a driving frequency omega. Now let's take a look at how the steady-state solution behaves for different values of driving frequency. Here are the plots of the coefficients a and b as a function of driving frequency. The red line represents the coefficient b and the blue line represents the coefficient a. On the x-axis we have driving frequency omega. The plot on the left-hand side corresponds to the system with larger damping, and the plot on the right-hand side corresponds to the system with a small damping. We will now consider some few limiting cases. First, if the driving frequency is much lower than the natural frequency of the oscillator, meaning we are somewhere in this region, we can see that the coefficient b is practically zero, and only a contributes. In this case, the steady-state solution is simply a times cosine function, which means the system oscillates in phase with the driving frequency. This scenario corresponds to the time evolution shown here. The graph represents the full solution, so the sum of the transient and the steady-state part. We can observe some violent oscillations at the beginning, which are a result from the transient part of the solution in the subcritical damping regime. However, after a while, these tiny oscillations decay and they leave only the steady-state solution. We can clearly see that the envelope function follows the cosine-like pattern corresponding to the steady-state behavior. What does this solution physically represent? Imagine holding a spring with a mass attached to the other end. In this case, when a driving frequency is very, very low, it essentially means that you are slowly moving your hand back and forth. And how does the system respond? Well, when the motion of your hand is very slow, mass and the spring basically follow your hand's movement, except that the spring is not perfectly rigid, so there will be some small oscillations around the instantaneous equilibrium position. You can even try this experiment yourself. Move a spring mass system slowly back and forth and observe how it follows your motion with small additional oscillations. And this is exactly what our solution describes. The overall cosine-like pattern due to slow hand movement plus the tiny oscillations at the beginning that decay away. On the other hand, when the driving frequency is still less than its natural frequency, but not by much, we are somewhere in these regions. In this case, we see that both coefficients a and b are non-zero, meaning both terms contribute to the solution. An example of the solution for this situation is shown here. Unlike the previous case, I cannot provide an equally intuitive explanation for the exact form of the solution. It simply looks like this. And there are actually many parameters that influence the exact shape of the solution. The amplitude of the driving force, the driving frequency, initial conditions, and so forth. So as we discussed, the initial conditions only affect the beginning of the solution, not the steady-state behavior. However, if this form of solution seems unintuitive, we can still see some important features. At the beginning, there is a transient solution, and that gradually decays away, leaving only the steady state after a sufficiently long time. Next case is, On the left-hand side, we are still below the natural frequency, but now we are very, very close to omega 0. So we are somewhere in these regions. We can see that both coefficients increase in this region, which is obviously reflected in the nature of the solution here. On the right-hand side, the solution corresponds to the case when the driving frequency is exactly equal to the natural frequency of the oscillator. In this case, we are working at this exact point. The coefficient b reaches its maximum value and a becomes 0. And we can observe how the system responds. The amplitude of the oscillation grows rapidly. This phenomenon has a name and is called resonance. We will discuss it at the end of the video in more details. From now, let's continue and examine the next limiting case. The solution displayed on the left-hand side corresponds to this region, where we are now above the natural frequency. In this case, both terms are non-zero, meaning that both sine and cosine function contribute. Again, I don't have an intuitive explanation for this exact form of the solution, but we still can observe general features. The presence of the transient part at the beginning, which disappears after a sufficiently long time. On the right-hand side, we are working in this region, where the driving frequency is much larger than the natural frequency. We can see that both coefficients a and b are practically 0 here, that the amplitude of the oscillations is almost 0, meaning that the amplitude of the oscillations is practically almost 0. If the frequency of the driving force were to go to infinity, the solution would be exactly 0. However, since infinity is not physically meaningful, we can imagine a very large but finite frequency, in which case the coefficients would be close to 0 but not exactly 0. And this is also visible in the solution. We can see tiny oscillations with small amplitude around 0. But what's happening here? Why is it that when driving frequency is very large, the system barely moves? This might seem counterintuitive, but it is absolutely correct. You can even try this at home. If you have a spring, attach mass to its end and move your hand up and down as fast as you can. What you will observe is that the faster you move your hand, meaning the higher the driving frequency, the smaller the amplitude of the mass will be. This is exactly what our calculation predict. What's happening here is that the system is trying to respond to rapidly changing external force. But because the force is changing so quickly, the system simply doesn't have time to react and ends up lagging behind. The net result is that the amplitude gets suppressed. Okay, we are done analyzing different kinds of solution. As we could see, family of solutions is very rich, and we can get all kinds of weird time evolutions, depending on the driving frequencies, force amplitude, initial conditions, and so forth. In conclusion, let's discuss the phenomenon of resonance. We have already seen when the driving frequency is very close to the natural frequency of the oscillator, the system responds in such a way that the amplitude of the oscillations grows rapidly. And we can actually calculate exactly what is the driving frequency at which resonance occurs. Again, I will not perform all mathematical operations step by step. I will only show the intermediate results and comment on them. But let's first rewrite the steady state part of the solution in a different form. In the first video on a simple undamped oscillator, we discussed the various forms in which the solution can be written. In particular, we saw that this expression, written as a sum of sine and cosine functions, can also be written as some constant r times cosine function with initial phase in the argument. The transition from one form to another is quite straightforward. We can, for example, decompose the cosine function using the sum and difference formula for trigonometric functions, and then compare two solutions. We recognize that the coefficients a and b can be defined in this way, and from this one can easily derive the expression for the coefficient r. I leave this for the audience as an exercise. The coefficient r is the amplitude of the oscillation, right? We can see that it depends on driving frequency omega. Here's a plot of the amplitude r as a function of driving frequency. One can see that a function has a maximum at some frequency. We can find this maximum by taking the first derivative of r with respect to omega and then equating it to 0, because at the maximum the first derivative is equal to 0 by definition. From this definition we can calculate the frequency at which this happens. This defines the resonance frequency. I'm not going to do that explicitly, but here is the result. We can see that the resonant frequency is not exactly equal to the natural frequency, but is slightly smaller. It is shifted by an amount that depends on the damping, by the constant gamma. If the damping is very small, we can neglect this term and the resonance frequency is almost equal to the natural frequency. However, for larger damping, the resonance frequency can differ significantly from the natural frequency. We can see this in this graph. The maximum of the amplitude is not exactly at the natural frequency, but is slightly less for small damping, the blue line. But as the damping increases, the maximum shifts to small values of omega. Alright, that's it for today. If you enjoyed this video, please like and subscribe. I will see you next time. Bye.